So I'm going to be talking about a paper that was written a few years ago with my student Zara Jafargoli. The starting point of our work is again the beautiful result by Patrascu that shows a connection between three-sum and listing triangles. Let me start by defining exactly the problems about triangles that will be important in this work, and we have seen them already, but I'm going to present them in a slightly different angle. So the most basic problem is perhaps that of detecting if there is a triangle in the graph. Okay, so I'm going to call this detect triangle. Okay, so you're given as input a graph with m edges. So the graph is parameterized by the number of edges, and it may be sparse. And you want to know if there is a triangle. Okay, which is the same thing as asking if there is a clique of size 3. Okay? So here, simple result by Alon, Eustwer, and Zwick shows that you can solve this in time m to the 2 omega over omega plus 1, where omega is the exponent of matrix multiplication. And this thing becomes if omega is equal to 2, m to the 4/3. Okay? Right? The problem that's more relevant for our work, however, is a variant of this in which you want to list triangles. Okay? I'm going to call this a list triangle. Okay? And again, you're given a graph with m edges, and you want to list m triangles. So it may be that the graph has fewer than m triangles. In that case, you are just asked to list all of them. It is possible to parameterize this problem by how many triangles you want to list. However, for all the points that I'm going to make, having this number to be m is sufficient. And here there is a recent result by Bjorklund, Pegg, Basileska-Williams, and Zwick.
Can you write a little bigger?
Right, bigger, okay. I'll do that, thanks. And Zwick, that gives the same bound, okay? So same. So again, they get m to the 2 omega over omega plus 1, which becomes m to the 4/3 if omega is equal to 2. Okay. Right. So and now I can tell you about this result by Patrascu again. So it shows that this bound here is tight for listing triangles, assuming that three-sum is hard. Okay. So Patrascu shows that. So if listing triangle is in time m to the 4/3 minus some constant, okay, minus omega 1, then three-sum is also in time n to the 2 minus omega of 1. Okay? So again, this time would be tight if three-sum requires quadratic time. Okay? So in this work, we were interested if you could give reduction in the opposite direction. Okay? And that's what we obtained. So in this work, we show that if three-sum is in time n to the 1 plus epsilon, then you can list triangles in time m to the 4/3 minus plus order of epsilon. Right, so this result does not give anything if 3-sum is just barely below quadratic time. You need a substantial improvement to get anything. If 3-sum happens to be in a linear time, then you get an algorithm for listing triangles which runs in time m to the 4/3, which is the same running time that was achieved in this recent work under a different assumption, namely that the omega is equal to O2. Both Petrasco and our work actually came before this improvement of listing triangles. Before we did not have anything which could reach m to the 4/3, even if omega is equal to O2. Okay, so one motivation for this work is that we've seen a number of other results which are based on the 3-sum conjecture. So it seems natural to ask what you can do if 3-sum happens to be easy. Okay, so I don't know of many such things, and here we show that you can get something about triangle listing. But there is another which is less obvious motivation, which is the one about variance of 3-sum. Okay, let me just try to put it here. Okay, so variance of 3-sum. So let me consider the problem which I'm going to call 3 XOR, okay, which is the same thing as 3-sum, but over the domain GF2 to some power t. Okay, so I can write that as given an n by order of log n GF2 matrix, do 3 rows sum to 0. Okay, so each row would be one of the elements in your input, and you want to know if there are 3 elements that sum to 0. Okay, so a challenge that I want to raise is this one. Relate 3-sum and 3 XOR. Okay? And we're not the first one to look at variance of 3-sum. I'm going to mention how it works in a second, but I don't know of other works that are concerned with just 3, with sums of 3. So what's the most basic possible relationship? Rule out that 3-sum is as hard as possible and 3 XOR is as easy as possible. Okay, so here is a specific challenge. Rule out that 3-sum requires quadratic time, but 3 XOR is in linear time. Okay, or vice versa. Okay, we don't even know how to do this. So what do? We show that, so in this work, we show that if this strange looking scenario holds, so if this holds, so if 3-sum is super hard but 3 XOR is super easy, then listing triangles has complexity exactly, meaning both upper and the lower bound m to the 4/3. So here I'm suppressing polylogarithmic factors. Okay, so how is this shown. So the proof idea is very simple to explain. So we are going to, we can re-execute the reductions for 3 XOR. Okay, so both the reduction in Patrascu's paper and the reduction in our paper works just as fine if you are dealing with 3 XOR instead of 3 sum. Okay? So that means that in that scenario, this would be the complexity of listing triangle. Why is that? Because if this thing was any faster than that, then by Patrascu's result, you will get the subquadratic time for 3 sum. And the fact that 3 XOR is linear time means that the complexity is not higher than this. Okay. And the same thing holds if you swap the roles of these two. Okay. So what I'm going to do now is to, oh yeah, so I want to mention other reasons why this challenge may be interesting. So let's look at variants of these problems when the number of summands is larger than 3. So if you look at 3 sum, you obtain the problem subset sum, okay, which is NP-hard. So you give a bunch of numbers, you want to have some subset sums to 0. If you do the same thing for 3 XOR, you get subset XOR, which is easy. Okay, if I give you a matrix and you want to know if some subset of the rows sums to 0, you're just asking if the rows are dependent or not, and that can be done in polynomial time. So this is in P. On the other hand, if I look at K XOR, and K is part of the input, so I give you a matrix, and ask you if there is a linear dependence with exactly K elements, this thing is hard. This is NP-hard. Okay, and that's because it allows me to know the minimum distance of a code, which is an NP-hard problem. And there is other work that looks at this type of variance of 3 sum when the number of summands is large, and that's by Bhattacharya, my server, Indic, Woodruff, and Shia. Okay. They look at the K sum over FQ for arbitrary fields FQ, and they they give tight bounds up to polynomial, assuming the exponential time hypothesis. Okay, so, but as far as I know, the result does not say anything for k equals to 3. All right. So what I'll do now, I'll give you a proof of this, this reduction. Let me start with the overview. So the proof is in 2 steps, both of which are fairly easy. Proof overview. Okay, so the first step is to show that if 3 sum is in time n to the 1 plus epsilon, then you can detect triangles in time m to the 1 plus epsilon. Again, I'm adding here a big O. And this reduction is fairly easy. In fact, it was done earlier by Peg and Peg, okay, in a different context, which we didn't know about. But so a technical contribution of this work is to make this thing deterministic. So the reduction is randomized. We managed to randomize it. So we make this thing deterministic. And there is some value of making things deterministic also because of the recent work that was presented here at the last workshop where they showed that some problems like 3-sum may not be strong ETH hard, and for that framework you need deterministic reductions. But I'm not going to say more about this. And the second step, which may be the more interesting one, shows that if you can detect triangles in time m to the 1 plus epsilon, then you can list triangles in time m to the 4/3 plus order of epsilon. Okay? So if you combine these two things, you get this reduction here. And this one here, the second step follows closely another argument by Wasilewska-Williams and Williams, where they give a similar reduction but for dense graphs. So a contribution of this work is to have a same reduction, but that works for sparse graphs, okay, which is a little more complicated. Okay. Sparse graphs is essential because we are dealing here with subquadratic time. By the way, I want to make a comment that I mentioned earlier that we re-executed the reductions also for 3XOR. In particular, we re-executed the one by Petrasco. So if you want to know about Petrasco's reduction, the variant for 3XOR, which is in our paper, is a little easier because in the context you have linear hash functions. So if you want to learn about it, you may want to take a look at that. All right. Is there any question about the plan? All right, good. So let me start with the second item. Okay, so 2. So I'm going to show now that if you can detect triangles fast, then you can also list triangles fast. Okay? And I will start by giving an overview of the earlier approach that I mentioned, and then I will highlight what's new in our work. Okay, so the first thing is that we are going to work with tripartite graphs. Okay, so if you have a graph here, which is a bunch of edges, like this one, I'm going to convert it into a graph which has 3 parts. So I'm going to triplicate all the nodes, and I'm going to repeat each edge 6 times, 1 time for every pair of parts. For example, this edge here now will go from here to here, and 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 from here to here. Okay. So this transformation makes the following recursion easier to understand, and it just blows up the number of triangles by a factor of 6. So it does not make a difference for listing triangle algorithms. Okay. So the approach is to use recursion. So we are going to split each, well, let me call it partition. I'm going to partition each part in two. Okay, so I'm going to take a subset of the nodes here, subset here, and a subset there. Okay, and this gives me this gives 8 subproblems. Okay, so one subproblem would be the one in which of the edges whose endpoints fall here, here, and here. Okay, and there is 7 others. And then you recurse on each subproblem. And when you recurse, you do 2 things. So the first thing is that you only recurse on a subproblem if it does contain a triangle. And for that, you use the triangle detection algorithm. So only recurse if there exists a triangle. And the second thing is that since we're all interested in listing m triangles, I'm just going to keep around m subproblems. So only keep m subproblems. All right, so now I'm going to make an assumption and then tell you how the proof will be finished under the assumption. So let me assume that each subproblem has m over 4 edges. Okay, I will tell you later how this thing can be ensured. In this case, you can finish the proof as follows. And finish as follows. So I just want to give you a sketch to give you a sense of how everything ties together. So the time, let me actually continue here. So the time of your algorithm would be, so every time you reduce the number of edges by a factor of 4, so it's a sum that goes from 0 to log base 4 of m of Si, where Si is the number of subproblems at recursion level I. Okay. And for each of these, I'm calling the triangle detection algorithm on a graph which has m over 4 to the I edges. So T is the triangle detection time. Right. And then what you use about S sub I is the following. So the idea here is to split the sum in 2, So if when this index here is small, then you just use the fact that S sub I is at most 8 to the I, because every time you have 8 subproblems. And if I is large, then we use the fact that since we just want m triangles, we only keep m subproblems. Okay, so we use that Si is the most m. Okay, and if you just pick the right threshold for small and large, you will get this time m to the 4/3 that I mentioned earlier. Okay, so that's the whole proof, under the assumption that every time the subproblem has m over 4 edges. And again, this thing is basically from the previous paper by Vasilevska, Williams, and Williams. And our main contribution is to port this to the sparse setting. And in turn, the main hurdle for that is the assumption that each subproblem has to have exactly amorph edges. So in their context, the graph was dense, so you just split the nodes in half, and this thing is automatically guaranteed for the right for the right measure. For us, it's not so immediate, but it's not particularly hard. How we ensure assumption. Okay, so first of all, we're going to pick the partition at random. Okay, so each node is going to toss a coin to decide which side it is in. So the partition is random. Each node flips a coin. And now let me consider one specific subproblem. So fix a subproblem which I'm going to call S. Okay, so what is S? For example, is the collection of edges whose endpoints correspond to nodes that always flip 0. Okay, so here the nodes that flip 0, 0, 0. So that will correspond to a subproblem. So e.g. nodes with coin 0, or 0, 1, 0, and so on. All right, so let me also define x at sub b to be the indicator variable of whether the edge E is in S. So xe is 1 if the edge E is in S, and 0 otherwise. Okay, so the expected size of the subproblem S is n over 4. Okay, it's obviously the sum of the xi, which is m over 4. So we are good in expectation, but we want to ensure that each subproblem has m over 4 edges. We would like that the expectation of the size of S is concentrated around its expectation. Is concentrated. To have this, in turn, it would be enough if the variables x sub b were, say, pairwise independent. So it would be enough if the x sub b were pairwise independent. Okay, because then I can use a Chebyshev inequality and argue concentration. However, the variables are Carnot. This is false. So, for example, you could have a situation like this. Now, the information that this node belongs to some part would affect potentially m edges or about m edges. So what we do to resolve this, we have an initial phase of the algorithm in which we go through high degree nodes. High degree nodes, we list their triangles. And then we remove those nodes. Okay? This is very similar to what is done and also in algorithms. You handle separately the ones of high degree. After you do this, you don't have extreme situations. However, the XB may still not be pairwise independent, because for that you need to remove pretty much everything. However, they are almost so. So the XB are not pairwise independent. But have limited dependence. Okay, I've removed the high degree nodes, so each variable here and now it's just going to affect m over a million other nodes, and that's enough to carry through an argument like Chebyshev inequality. But limited dependence, and this is enough for Chebyshev. And gives you the concentration that you want. Okay, so and if you want to make this thing deterministic, you can use a standard almost pairwise independent sample space and go through every seed and try every partitioning and pick the best one. Any question about this? Okay, so that's it for part 2. So now I will tell you about part 1. Okay, so here we have shown how if you can detect triangles fast, you can also list them fast. Now I will show you that if three-sum is fast, so it's in time n to the 1 plus epsilon, then detect triangles in time m to the 1 plus epsilon. Okay. All right, so as I mentioned earlier, this basic randomized idea is also in this paper by Peg and Peg, although in a different context. So here's the idea. So we're given a graph. So we're going to pick a random integer x sub u for every node. Okay. And then the three-sum instance is the following. The three-sum instance will be the set of numbers x sub u minus x sub v, such that x sub v is an edge in a graph. So here I'm thinking of the graph as being directed. It doesn't matter if the graph is undirected. You can write that as a directed graph with edges in both directions. So for the analysis, so clearly if there exists a triangle, then the corresponding three numbers will sum to 0 because everything will cancel out. So this is easy. If there is no triangle, then every three numbers that you pick will correspond to a non-zero linear form in the axis. And so with high probability over the choice of the assignment to the axis will be non-zero. Okay, so any three numbers, it's it's a non-zero linear form for polynomial, and so you get non-zero with very high probability, and you can do a union bound over all possible choices for these three numbers. Any questions about this? Okay, so So now we'll tell you how this thing can be made deterministic. So how we make it deterministic. So the bottom line here is to find the collection of numbers which have non-trivial solutions to a certain type of equations. Okay, so need a collection of numbers with no non-trivial solutions. By non-trivial means that the numbers are not repeated. To this equation here, x1 plus x2 plus x3 is equal to x4 plus x5 plus x6. Okay, so that's the type of equation that you get from the sum of three numbers here. So if I have a collection of numbers which have non-trivial solutions, I can just assign those numbers to my nodes, and if there is no triangle, you will get a 0. Okay, so this seems something like it's the bread and butter of additive combinatorics, and in fact there is a large literature. I'm sorry.
You have to worry about?
No, I think that's that's the only that's the only type of solution that I need to worry about. Yeah, for threesome, yeah, for triangles. So the additive combinatorics, there are many papers that give upper and lower bounds on the size of such collections. However, as far as I know, none of those results give you a construction that runs fast. Okay, so you can extract maybe a quadratic time construction of those numbers, but that would be not good enough for us because we need to work in about a linear time. Okay, so this is not a linear time construction, or not even close. Okay, if any of you knows of a reference, otherwise let me know. Okay, so instead, we use a different approach. We show how to use combinatorial designs to construct such collections. Okay, so we are not going to get the same precise bounds, of course, on the size of this collection, but it will be good enough for us. And using a certain construction of designs, I will be able to produce these numbers in a linear time. So we have seen already several papers with more uses of combinatorial designs, and this is one more. Okay, so the design, I will pick a collection of sets, M sets, where S sub I is a subset of a universe of size order of log m. So just think of it as having order log n bits in the characteristic vector representation. And the property that I need is that S sub I intersect S sub j would be at most say the size of S sub I divided by 10 for every I and j. So the intersection of any two is fairly small compared to the size. Okay, and the number of sets has to be exponential in the universe size. Okay? If you have this, then what you do? Then my number xi, has a decimal representation which is equal to s sub I. So the s sub I is decimal representation. Decimal representation of x sub I is given by s sub I. Okay, so just think of these sets and put zeros and ones for x sub I. And now I claim that with this you don't have any solution to this thing. And why is that? Because pick any candidate solution. Let's look at, for example, at x sub 6. Okay, this is some set. Okay? And it has 1 in certain places and 0 in others. And when you make this sum, there will be no carry in the decimal representation. So it's all a matter of whether the ones that appear here can possibly cover the ones that appear in X, and that's not going to happen because I have this requirement here. Okay. So what do we know about construction? So the first construction of designs with these parameters explicit is in the seminar paper by Nissan and Biderson. But again, that's a greedy that's an iterative construction which has a time exponential in M. Okay. While we need quasi-linear in M. So we use a different construction, which we have in this paper from a while back with Gutfreund, which we can get the above parameters and time order of M. Okay, it's a construction which is based on combining error corrector codes with designs which are obtained via brute force. Okay, but I'm not going to give you the details now. And that's it for me. Thank you.
Any questions? People start getting tired in the afternoon. So let's take any questions. Fine, thank you.
Thank you.